Let's look at the systematic treatment of equilibrium. And let's use calcium fluoride as an example. You may know that calcium fluoride is not very soluble in water. It has a relatively small KSP. The KSP is 3.9 times 10 to the minus 11. And you probably know that we could write the equilibrium expression for this reaction as the calcium concentration times the fluoride ion concentration squared, since there's two fluorines. And you've probably already gone over in a general chemistry course how to solve one of these equations for the calcium concentration using an ice table. So let's briefly review that. Initially, we don't have any of the calcium or fluoride in the solution, but we will dissolve X amount of the calcium, and when that dissolves, there will be 2X of the fluoride, and so 0 plus X is X, and 0 plus 2X is 2X, and then we could plug these numbers into our KSP, and I'll do that right here. And that should be 4x to the third. And then if we solve for x, which is also the concentration of calcium, we would get this. Point 0.002136 molar. Now you might think, oh, that's great. We have the answer for how much calcium is dissolved. But maybe you remember that fluorine can undergo an acid-base reaction, or I should say fluoride. And let's write that out. So now we've written out the Kb expression for fluoride reacting with water. And the Kb is 1.47 times 10 to the minus 11, or at least that's what it computed to from the sources that I have. And if we write out the expression, then we would have HF concentration times the hydroxide ion concentration divided by fluoride ion concentration. Now the problem with saying this first equation is true just by itself is that the fluoride, when it's in water, will a little bit at least convert into HF. And when a little bit of this turns into HF, then more of my calcium can dissolve. That would make more fluoride, which in turn could make more HF. And so we have this kind of loop. And so we'll need some more equations in order to solve this. So we've got two. We've got the KSP And we have the Kb expression for HF, or F negative, fluoride. But we'll need a few more equations. Now, anytime we have hydroxide, we should look at the Kw expression. So let's do that. So now we have Kw, that's 1 times 10 to the minus 14, is equal to the hydroxide ion concentration times the H plus concentration. So we've got several equations here, and we'd like to be able to solve for the calcium ion concentration, but this is not going to be enough, because if we count up the number of variables, we have hydroxide, hydrogen ion, fluoride, HF, and calcium. That's 5 different variables. We only have 3 equations. And in order to solve this, we'll actually need 2 more equations. That way we have an equation for every unknown that we have, and then it's possible to substitute and work it out. So we'll need 2 other equations. We'll need a mass balance equation, and we'll need a charge balance equation, but I'll get to that in a second. So for the mass balance equation, we're going to take advantage of the fact that the calcium and the fluoride have a relationship, a numerical relationship, because they started out connected to each other. Every calcium has 2 fluorines. Now those fluorines can become either fluoride, F negative, or it can become HF. So here's how this is going to work. We have a relationship between those. So I'm going to total up all of the places that the fluorine can go, and I'm going to set that equal to the calcium concentration. Now, just like this expression is not correct because there's a 2-to-1 ratio between the calcium and the fluoride. And it is tempting to write 2 in front of the fluorines because there's twice as much. But these are concentrations. So we would expect that since there's twice as much fluorine, that there should be a higher concentration of the fluorines versus the calcium. So in order to make that up, we'll have to multiply the calcium by 2. So now these 2 sides of the equation are equal to each other. So now we have a mass balance equation. Now let's look at a charge balance equation. The charge balance relies on the fact that we should have an equal amount of positive and negative charges within our solution. So since calcium has a 2 plus on it, we're going to multiply that that concentration by 2. And then we'll add up our other positive charges, which is H plus. And then we'll set that equal to all of the negative charges because the positive and the negative charges should be equal to each other. Now we have a mass balance and a charge balance equation. Now, once we have all of these, we have our KSP expression, we have KB or KA, either works really, KW, a mass balance and a charge balance. It is possible to now solve for the calcium ion concentration. It's just not that easy because there's a lot of equations and there's squares and a whole bunch of other pieces there that make it a bit complicated. And so what we'd rather do is put all of this information into a computer, like a spreadsheet, and have that calculate it for us. So I did that, and I will show you kind of what to type into each equation and how to make this work. So the first thing that we do is we have our calcium concentration, and we're going to put in a guess for that in our spreadsheet. So let's just fill in what we have up here as our GChem answer, right? So you just put a guess in. Kind of an initial concentration. And I would start with the GChem answer, or with the answer without all of this, because it's going to be close. And then we want to have a way to solve for each of the other pieces with relation to the calcium concentration or another cell that's coming down. So in this next area, we're going to calculate the fluoride ion concentration. And I'm going to use the KSP expression to do that. And so let's solve for fluoride using KSP. Well, I would take calcium, I divide it over on this side, and then I'd need to take the square root. So, square root of KSP divided by my calcium concentration. So I'll take, if I'm working in Excel, I'll take this cell and I'll reference it right here, and I'll just put in the KSP. So now whatever we guess here will calculate a concentration for the fluoride. It won't be correct, but it will be correct according to this KSP. And then we'll fix it as time goes on here. Then we can calculate the HF concentration based off of the mass balance equation. So I'm just going to solve the mass balance equation for HF. Now in this, I can just take this cell, whatever number's in here, put it in there, and I can reference this whole piece and put it in there. And then it will calculate a value for HF. Next, I need to calculate the hydroxide ion concentration, or H+, depending on which way I want to do it. But I'm just going to solve my KB for hydroxide ion concentration. So I just reference this cell right here, and I reference that cell right there. And now I have a hydroxide ion concentration. And then I'm going to calculate my H+ based off of KW and the hydroxide ion concentration. So I'll just reference the cell above it. Now you might be saying to yourself, oh, that's great, this looks good. But of course, there's going to be a big error in this calculation. And how do we actually adjust for that? Well, we're actually just going to use the charge balance equation to correct everything else. And so what we'll do is we'll set up the charge balance so that it should equal 0. So in this last cell, we'll call this error. Let's see here, 2 times calcium plus H plus. And then I'm going to solve this. I'm going to move everything over to one side so this will equal 0. Minus hydroxide ion minus fluoride ion. And this should equal 0. It won't because our guess is bad or not quite good enough, but it should equal 0. And if you're working in Excel, you can go into a little feature called Goal Seek. And you can tell it to set this cell equal to 0 by changing this cell. And it will go through and it will change this one until this is sufficiently close to 0. And when I did it, it didn't do that much because Excel thinks small numbers are close enough to 0. So I ended up taking this whole piece and multiplying it by 100 or 1,000 or something like that, just to increase the sensitivity so that Excel would go and actually calculate it better. And when I did all of that, I got the calcium concentration to be 0.002137.2, which, if you look up here, is very close to what we just calculated without doing all of this extra work. 0.002136, 0.002137, very close to each other. And you might say, wow, we went through a lot of work just for not a whole lot of difference here. And that's true in this particular case. But what would happen if we, instead of having just put this in pure water, we put this in a buffer? And that buffer had the pH set to 3. Well, if we put this in a buffer, then we can no longer use the charge balance equation because there's other charged species contained in a buffer that we will not be able to account for in the charge balance equation. But that's okay because it's reducing the number of variables that we have to solve for, because if it's in a buffer at pH 3, we'll know the concentration of H plus and the concentration of OH minus. So that simplifies our problem. And if we do that, I actually calculated the calcium concentration to be quite a bit higher at 0.0039 molar, which should make sense because that is a relatively acidic solution. And so we should be pushing this Kb equilibrium forward more, which will cause more of the fluoride to be used up and end up in the HF form. So that will adjust where the equilibrium lies. So this is how to do a systematic treatment of equilibrium problem. The main feature of this is actually just writing out the KSP, the KBs, the KW, the mass balance, and the charge balance equations. All of the equilibrium equations for all of the reactions that are involved in the equilibrium, all of the Ks, KSP, Ka, KW, whatever. all of those. Writing out a mass balance equation, relating hopefully a few of the pieces to each other, and writing out a charge balance equation. After you have all of those correct and written down, it is possible to solve a system of equilibria. And hopefully you don't have to do that by hand and can instead use a computer to do it for you. Now, we did still make some simplification here, and we did not include any of the effects of activity on the solution. You can do that, and I would recommend, again, using a computer to compute that. But hopefully this gets you going in the right direction on solving these systematic treatment of equilibrium problems. And with that, we'll see you in the next video.